Good afternoon, it's Charlie ZL2CTM. Well, I've just got back from being away for a couple of weeks, and I've had an opportunity to be in the shack for a couple of days, which is nice, and have just been sort of pottering around with this software-defined radio based on the Teensy 3.5 and the audio shield and the audio library that's been built up by Paul for that particular microcontroller. I'm not quite sure exactly where I'm going with this. At the moment it's just more of a, I guess, bit of an exercise in playing around with the various techniques of generating and demodulating single sideband, as well as other modes in due course. But in terms of it turning into an actual radio, I'm not entirely sure where that's going. But hey, it's all good fun. So in terms of some changes since last time, what I have added is a couple of 600 to 600 ohm transformers from the output of the SBL1s and the line in to the audio control panel. I did that just to well and truly break any ground loops, and it also cut down on some what I was terming DSP whine, but I think it was something else. But suffice to say, the addition of those transformers, which I must admit is standard practice with these sorts of radios, certainly helped with that. And that's really, in fact, that is the only change since the last video. So in terms of software, I just wanted to sort of cover off on a couple of things I've been sort of reading up on and playing around with. And I apologise that I'm sort of filming the screen here, but this is just sort of a video log, and it's the way I'm going to do it. Again, this is not a tutorial. This is just purely sort of logging or talking about what I've been playing around with to sort of encourage others, I guess, to give it a go. So sort of two things I've been playing around with. One is the phasing technique, and the other one is the weaver, or also known as the third method for generating SSB. Both these configurations here are for the receiver, and flip it around and it's for the transmitter. For this particular build, I'll be playing around with receiving first, and then I'll convert it over into transmitter. So in terms of the phasing technique, the I and Q channels on the left hand side there are the inputs from the SBL1s through the two isolating transformers. I'm not going to go into the maths here for this. There's some really good texts online that talk about the phasing and the weaver with great diagrams of plots showing how the maths works out to recover the audio or our intelligence at the right hand end. I don't intend to do that here. It's just I guess just giving a summary of what I've done, and I'll show you what I've done there, and we'll go from there. So that I in 2, or the I in phase, and the quadrature signals coming in, so those are 90 degrees out of phase. In order to recover either the upper or lower sideband, we need to introduce another 90 degrees phase difference between those two signals before we either add or subtract them to recover either the lower or upper sideband. To do that, I'm using two Hilbert transforms, which is the common way of doing it. In some of the text you'll see that being done in one line only, doing a full 90 degrees. The problem with that is you get a delay in one line which doesn't match the other half. So a lot of texts talk about splitting that overall 90 degrees phase shift by doing 45 degrees plus on one line and minus 45 degrees another. In other words, a total of 90 degrees phase difference. In this particular case, these Hilbert transforms, I used the Iowa Hills software, which we'll have a look at in a sec. That's free software you can download from Iowa Hills to generate the coefficients that will fit into the two FIR filters within the Teensy. I had those two. Okay. If you look at what others have done with using the Teensy to do SDR, some have brought the audio in at a much higher frequency, i.e. around that sort of 10 to 11 kilohertz, and then heterodyne that back down to the audio frequency before punting it out. I've just elected to just play around with it at this stage and just do the Hilbert transform directly down at audio. But in an attempt to mitigate some of the noise that is around DC, I elected for that low pass, well, this is actually a band pass filter here, which is also introducing the plus 45 and minus 45. That bandwidth is 2700 Hertz, and I've got it set up to be from 300 Hertz to 3 kilohertz, with a center frequency of around 1.53 kilohertz. In terms of the Teensy itself, in terms of how that's wired up, what I'll probably do is I'll just go through the two techniques, and then we'll look at the software. You'll recall from a previous video, this piece of software here is online. It's from the PJRC, the supplier of the Teensy, and this particular design tool here is the Teensy audio library design tool. And what it allows you to do, on the left hand side, it has all of the various objects that you can use within the library, and you can drag those onto the design field here, and then wire them up to do various things. What I've depicted here is both the phasing, and later on I'll talk about the Weaver technique. So the way I've got it configured with the Teensy, I've got the audio coming in, the I and the Q from the SBL1 coming in from the line-in ports of the audio panel, going into two Hilbert transforms. If I click on those, and on the right hand side you can see that they are FIR filters, and it talks to you about how you can assign over here the coefficients. So you define the array length and the actual coefficients themselves, and then you can set up that digital filter. So suffice to say, I've got two of those, one for the plus 45 degrees and one for the minus 45 degrees, and then the output of those two filters then get combined into a summer. And again, if I was to now click on that summer, I can see on the right hand side how to manipulate that as an object within the C program. And what's of use to us, which we'll see in the code, is this gain here. So what we can do is we can say for any one channel, so channel 0 and 1, so 0 we can say is level 1, so in other words it just gets taken straight through. And then if we want to do subtraction, for example on say channel 1 coming in here, we could say channel 1 comma minus 1. So we've actually now inverted the input, and now if you were to sum that inverted input with the other input, you've got essentially subtraction. So that's the method, as you'll see in the code, for very easily converting that into either sum or difference to recover either the upper or the lower sideband. The other method I've been playing around with is the Weaver method, or also known as the third method of generating SSB. This is the demodulation configuration. A little bit more complex, but not overly difficult. Again, won't go into the maths here, but some interesting things you have to do to make this particular method work. Again, this dotted line here is the input to the Teensy, and the left hand side is the hardware, which we saw before. So the SBL, so again the SI5351 providing those two quadrature signals to the SBL1s. But interesting enough, for the SI5351, you need to set it to be your frequency of operation in either plus or minus, depending if you want to recover the upper or the upper or lower sideband, plus half of your desired audio spectrum. So if we were to have 300 Hertz to 3 kilohertz, that's 2700 Hertz total. Divide that by 2 is 1350. So in this particular case, we're going to recover the lower sideband, so we need to have subtraction. So as you'll see in the code in a sec, we set up the SI5351 to be our frequency of operation minus 1350 Hertz, which is quite interesting. The I and the Q channels then, as they enter into and are digitized now on the Teensy, get fed to two low pass filters. They again are fur filters with the coefficients designed from within the Iowa Hills, which we'll look at in a sec. Being low pass filters, the interesting thing here is the minus 3 dB point for the knee of the curve is set to again half of our desired bandwidth. So in other words, 1350 Hertz. The output of those two low pass filters get then mixed with two oscillating signals and then fed out. Now, interesting enough, so these two oscillators here again set to a frequency of oscillation of 1350 Hertz, and then so it's the same frequency there, but they are 90 degrees out of phase. So one is cos and one is sine. The output of those then goes into again another summer, and either you add or you subtract to recover the desired sideband. Interesting enough, over here, so we're going for the lower sideband, we would be doing subtraction, so it'd be the frequency of operation minus 1350 Hertz, and then over this final summer here, it would be subtraction also. If you want upper sideband, that would be an addition, and that would be addition. So again, quite different from the phasing technique, and I've also implemented that as an example program, which we'll bring up as well. So that's the lower of the diagrams there. Again, our audio is coming into the Teensy through the line in. It's going to two low pass filters. Again, if we were to click onto those, you would see that they are again fur filters from within the library. You see on the right hand side, and then those are feeding into two mixers. Within the audio library, they are multipliers. So if we click on that, we can see on the right hand side the object name is actually an audio effect multiply. So multiplying is provides or produces the same effect as a mixer in the analog domain. Here goes our two oscillators. Those are just straight sine wave oscillators from the left hand side there, and the output of those go through to again a summer and then out to our headphone jack, which is the same as what we had for the phasing technique. Exactly the same method as we described before for inverting that second input to give us either addition or subtraction. So before I go look at the code, I'll just sort of nip down and have a quick look at the Iowa Hills software here. So again, this is free software that's provided from the Iowa Hills. The left hand side one here is for creating Hilbert transforms, and the right hand one there is for a straight fur filter. I won't go into it too much here. There is another video I've had up online for a while which talks about using this. It's reasonably straightforward. The only trick really is to make sure that the sampling frequency matches what's required for the Teensy audio panel, in other words 44117. I'm using 100 taps for both the Hilbert transform filters as well as the low pass filters in the Weaver technique. And then up here is our phase add. So at the moment it's on minus 45 degrees there, and if I make that plus 45, then the coefficients will be set up for the other phase shift. I've just optionally selected sync. Again, I haven't optimized any of these codes or any of these filters here. This is purely just an initial play around to see how it works. I also, if you look online, there's quite a few forums, certainly within the PJRC website, talking about 32-bit versus 16-bit maths. I haven't done any of that at this stage. This is just purely using the audio library as it comes, so vanilla. So, and that's all working on 16-bit words. Right, so over here on both these here, I've clicked the coefficients, and you can see here the coefficients have been generated once I push calculate. Then it's just a matter of going control later to copy all those, control copy, and we can then move those and prepare them for inputting into the program. Right, so like I say, both the software is free, certainly easy to use, and a good way of generating the coefficients that then get fed into the sketch, which ultimately then gets loaded into the Teensy to drive the DSP. Right, so up on the second screen here we've got the two programs. I suspect that's probably not overly easy to read, but that's not really the intent. What do I want to do here? I probably won't go into too much detail here. I will put both of these programs up online to have a look at. But if we were to say just go to the phasing technique, let's do that, shall we? And have a quick look at that. You'll see how it is really easy within the library that's provided by Paul to set up these filters and to make it all work. Without going into too many details, you'll recall that we just saw before the audio library design tool, and we had a pictorial picture of the filters and the mixers and the lines going between them. This is how it's set up here. So I'll stick with the terminology that came with the library, these patch cords. So that's akin to the old-fashioned telephone exchanges where you had patch cords going between inputs and outputs. And you can see here that our audio input left goes to our Hilbert transform plus 45. So that's a name that I have given that particular object. So that's audio filter fur. It's a fur filter, and I'm calling it the Hilbert plus 45. I have another fur filter which I'm calling the minus 45, and then I've got another object, the audio mixer, which I'm notionally going to call the receive summer. And as you can see there, so that our input goes to the Hilbert transform left, our right channel, which is our quadrature channel, goes to the minus 45. We then set up the output of those two filters. So there goes the plus 45 output goes to the summer channel 1, and then the minus 45 degrees output goes to the summer line 1, and then the output of those summer goes through to the headphones. I'm only using the left channel on the headphones, but I've just sort of kept both the left and right there, noting that the right is not actually being used. Very similar for the Weaver. So if I was just to find my mouse, come on, there it is, and then moving down to here, you can see there that it's exactly the same process for configuring the various patch cords to create, or more the point, to code the output of that design tool. Not going into great detail here. The input is going into our what I've called the receive in-phase low-pass filter, which is a fur filter. I've got that second one for the quadrature low-pass filter. There goes the two multiply objects there, which are our two mixers, one for the in-phase and one for the quadrature. There goes our two waveforms, which are the two oscillators, which I'm just notionally calling receive I oscillator and the Q oscillator, and then that ultimately that mix at the very end. So there goes the objects, and then there's the wiring them up, so to speak. So audio input, if we just go for one channel, audio input goes to the in-phase low-pass filter. The output of that low-pass filter goes to the mixer. We also have going to the same mixer here the oscillator, then the output of that mixer going to the summer, and then the summer going through the headphones, and same for the quadrature channel. So yeah, pretty straightforward. I'll put this up online rather than going into details here in terms of how to turn on or to the dot begin those particular fur filters, and also these coefficients. So these coefficients here came from the Iowa Hills software, and just running it through a short script to append the short brackets, this bit here, just to configure it correctly for that. I'm not entirely sure how to share that, but it's just a short script to automate the addition of that to configure it correctly. So what I'll do now, I'll just arc up the the test transmitter, and we'll just have a little listen to how they compare. Again, these programs or these filters are not optimized in any way, shape, or form. This is just straight vanilla having a bit of a play. So just going to key that transmitter, and we should start to hear coming through. So what I'll do for a start is I'll just make sure that we have up online or pushed in the phasing receive. So I'm just going to now push into the Teensy, which we'll see that update, the phasing receiver. Right, so the phasing receiver is now up and running.
Southerners standing out making it clear that they didn't stand with them.
And just playing a, I think it's the This Week in Technology podcast from the Twit network, and just transmitting that.
Protest, the police were there. And I can promise you.
Again, not optimized. I'll just cease transmission and then change to the upper sideband. So that's now on the upper sideband. Just a little bit there still coming through, and then back to lower sideband. Much better. Again, as I just said before, I haven't optimized any of the levels coming in. It's not unusual to try and vary the levels coming in to get better suppression of the unwanted sideband. It's also quite interesting too, looking at the literature on the phasing technique, the difficulty in having a constant or the same performance across the whole band or the bandwidth of the two Hilbert transforms. And there was some suggestion that the Weaver technique provides superior performance. But again, I can adjust in software the amplification of the two audio signals coming in an attempt to better balance that out. Haven't tried that at this stage. This is just purely throwing it on in and seeing how it goes. Okay, so that's the phasing receiver. I'll just now punch in the Weaver, upload that, and we'll see that come in a sec. Right. So that's now the Weaver.
And I somewhat fear that every site is going to use to exploit it to push their own agenda.
So that's,
video games.
again, if I was to cease transmission and change sideband, it's there again. Nothing's been optimized.
Much to blame is video games.
And then back to lower sideband there.
It's not more. If you talk about somewhere that's fostering a culture and propagandizing it.
On-air signals are pretty good too. This is midday here, so the 80 meter band is down, and I don't have anything set up at the moment for the other bands. So yeah, so suffice to say that it's been quite interesting to just I guess initially start with the software and just giving an idea of how it all sort of plays out, and sort of learning a little bit more about the two methods. As an aside, we mentioned before about recovering both the lower sideband and the upper sideband. If we just now look at this here, let me just zoom up on that. So we talked about the summer having two inputs, which we can see here. So at the moment the received summer, the gain of the 0 channel, which is the first channel, is a gain of 1, and in the summer for the gain of the second channel is -1. So I'm now inverting the second input, and the output is then essentially subtraction. If I was to recover the upper sideband for both, then I would change that second line there to be 1, 1. In other words, both would be added together as opposed to subtracted, which is nice and easy to do in software. I've already got the switch wired in, and it's just a matter of reading that switch, and then in software changing that second line for the gain of that particular receiver. So sort of moving forward from here, I might just sort of convert now into a transmitter. So for that, we're looking to use the line out of the audio panel there, and then feeding this thing backwards through the system. So line out, so that the microphone input to the audio panel will be the microphone, funny old thing. We'll then feed it through the DSP in reverse order, and like I say, pop it out, line out, and just feed it back through here. So it'll be mixed up to our desired frequency, combined there, and out she goes. And also something to work on in due course will be the HMI. Still debating about the usefulness, I guess, of the spectrum. The bandwidth, I understand, is 44 kilohertz, but we're only sampling up to 20 odd or 22 kilohertz. So yes, a tuning aid. I would agree it would be a tuning aid to have a spectrum down here, but in terms of getting a good understanding of what's actually being transmitted across the band, that's certainly not the case at all. Certainly nowhere near what you'd get out of a good modern day SDR radio. But that's just the way it's been wired up. I shouldn't say that's the wired up, that's just the limitations of using that particular board and using audio as an input. Okay, I'm starting to ramble here, so I won't say too much more. Like I say, just sort of playing around. Very, I will say, very easy to use that library, and conceptually wiring up in software the various blocks to make up the receivers, either the phasing or the receiver or the weaver, nice and easy. The Iowa Hills software, again, nice and easy to use, and with that script, nice and easy to quickly sort of change the characteristics of the filter, very quickly then throw it up into the program, and then throw it on in to see how it works out. A better way to do this would have these pulled out and put into an H file, but at the moment it's not taking up too much room, so I'm quite happy to leave that as is. So weaver on this side, and then the side here is the two Hilbert transforms. So we've got the plus 45 degree one with its coefficients, 100 of them, and then the minus 45, the 100 coefficients here. So it's not taking up too much room. At the moment, the two programs are only taking up 8% of the Teensy's memory, which is good. Okie dokie. I will leave it there. I will say too that that quadrature output of the ESI 5351 seems to be working well. So certainly happy with that, which is nice. What else is worth mentioning? No. So like I say, I think I'll just keep playing around with converting. I think for now I'll park the weaver as an interesting exercise. I'll just park that to one side and continue working on the phasing receiver. Excuse me. And basically convert it over to a transmitter, and then I can always double back around and look to better optimize the coefficients and the levels coming in to better suppress the unwanted sideband. But like I say, it's very easy to vary the inputs there, which is good. Okay, I'll say 73s there. Put this on up, and we will see you next time. Okay, cheers all.